Connor Wilson, and this is my final project for REE 413 Electrical Power Conversion at the Oregon Institute of Technology. For this project, I'll be reviewing and narrating my analysis of a Simulink model of a 100 kilowatt grid-connected PV array. So I'll give a brief overview of what this array consists of, component-wise. Starting over here at the generation side, we have a PV array that connects to a boost converter. This boost converter is connected to an MPPT controller, which controls the switching mechanism. The boost converter is also then connected to a 3-level voltage source converter, which converts that DC signal to an AC signal. The signal then passes through an inductive block and a capacitive block, which then filter out the AC signal harmonics out of the AC signal before it's fed to a transformer that boosts the voltage from 260 volts AC to 25 kilovolts AC that will be then sent to the grid. I forgot to mention that the voltage source converter is connected to this voltage source converter control algorithm up here in the right side. Now going back to the generation side, we have our PV array, which consists of 66 parallel strings of 5 modules in series, with each module having a maximum power capability of 305 watts. Now the environmental conditions over here on the left will affect the output of this PV array, and they are varied throughout the experiment. The irradiance will start at 1,000 watts per meter squared, and then drop down to 250 watts per meter squared during the experiment, while the temperature starts at 25 degrees Celsius and will jump up to 50 degrees Celsius. If we could take a quick look at this graph, we will see that we can see how that irradiance changes throughout the experiment. It starts off at 1,000 and gradually drops down to 250 watts per meter squared and then back up to 1,000 watts per meter squared. The temperature stays relatively flat at 25 degrees Celsius and then jumps up to only at the end to 50 degrees Celsius. Going back to our schematic, the output of this PV array then goes to a boost converter. And there's a few key components in this boost converter. We have a capacitor, an inductor or switch, and a diode. The capacitor has a capacitance of 100 microfarads, which is an pretty appropriate value if we take a look at the boost converter's output voltage, which shows that with this capacitance you get a voltage ripple of about 4.5 to 5 volts, which, when the numbers are crunched, produces a 1% voltage ripple, which is completely acceptable for a typical boost converter. Going on to the inductor, we can take a look at the inductor current, because the inductor current will determine the size of the inductor will determine whether the boost converter is operating in continuous or non-continuous conduction mode. Now, if we take a look at this current, the current stays positive. It drops down, but it stays positive during the entire simulation, which then suggests that the boost converter is operating in continuous conduction mode during the entirety of the simulation, which then also suggests that the inductor was sized large enough to prevent discontinuous conduction. So that is appropriately sized. Going on to the switch and the diode, both are pretty typical specification-wise. It's a little odd that neither of them were provided with a forward voltage drop. I'm not sure if the internal resistances were meant to account for that voltage drop, but typically for a semiconductor device, you'd want to see a voltage drop of 0.7 volts, something along those lines. We will be wrapping up the first part of this first video for the project shortly, but the next aspect that we'll probably be going into is the algorithm for the MPPT controller, and then I'll discuss the inverter and the grid connection for this system. All right, thank you, and I'll see you in the next video.